Okay guys, welcome back. We are launching into organic compounds. Just to set this up, I'll remind you that a compound is different than a molecule because a compound has more than one atom that makes it up, and that an organic compound is different than an inorganic compound in that it has carbon, with that one exception of carbon dioxide, right? Carbon dioxide is an inorganic compound. But let's stick to these organic compounds. If I were to ask you about the organic compounds that you might look for or try to avoid in the foods that you eat, because we are an organic life form and we consume organic life forms to basically deconstruct and build back up the human body, right? The simple way of saying that is when I go and eat an organic food item, right? Like if I eat a chicken breast or I eat salad or whatever, I am getting organic materials from those other living things, right? So what are the things that you look for in the foods that you purchase at the store? What are the things that you might want more of or less of, okay? And one of the things you might think about would be lipids. Now, you probably wouldn't say lipids. A lot of people will just say fats, right? I didn't want something low fat, or I don't want any fats. But fats, lipids, which is what we're going to refer to them as, are a major group within the organic compounds that make up our body. We need fat to a degree, okay? Fat is a healthy molecule to have to a certain concentration. It makes up every cell in our body, that basic unit of living matter. Okay, so lipids are an organic compound that contain carbon and a bunch of other atoms. Another thing you might look for, or try to avoid, depending, might be carbohydrates. All right, so you have your carbs, right? People talk about simple carbs. People talk about complex carbohydrates. Maybe they're trying to get more of one kind or another, right? Another way of talking about carbs might be to talk about sugars, right? Sugars are a kind of carbohydrate. All right, the other thing you might try to find in your food and make sure you have enough in your diet would be proteins, okay? So proteins would be another key thing to look for. And on average, the average American gets more than enough protein. You might see differently around the world, where sometimes there's not enough protein in a person's diet. But the last thing, and you probably don't look for this in your food, would be nucleic acids. So nucleic acids would be actually a more general term for DNA. And I'm sure when I say DNA, a lot of people perk up and they know what DNA is. But nobody's looking for DNA or nucleic acids in their food. DNA is a basic molecule that is necessary in a living thing, but it's seldom that we're looking for it. But it's absolutely in our food items, because if you eat something that was once living, which is basically everything in our diet, then you are, or any organic item in our diet, then you are probably eating DNA and nucleic acids. All right, so let's dive into each one of these. What I want you to realize now, before we go too much further, is these are the things I want you to know about the organic compounds. I want you to know the names, be able to list the 4 major groups that we just went over, okay? You'd want to know the elements, you know, carbon, oxygen, those kinds of things. You want to know the basic elements you would expect to find in each one of these organic groups. So that's 2, right? The name, the elements. I'd like you to know the basic function, okay, of each of the molecules in each of these groups, okay? What is the big thing we get? Or are there more than one thing that each of these groups allow for us to be able to do? And finally, the 4th thing would be, I'd want you to know the basic building blocks, the smallest unit that needs to come together to make a protein? Or what are the basic units that comprise a complex carbohydrate or a DNA molecule? Okay, so in a nutshell, the names, they're right here on this slide, right? The elements that make them up, the functions they provide, and then lastly, I'd like you to know the building blocks for the various groups. Okay, so let's dive into lipids. Let's knock that one off first, okay? So first thing I want to show you guys is a lipid molecule. What makes up a lipid molecule? And one thing that we'd say, and this is right off talking about building blocks, okay? I see a glycerol molecule. 1, 2, 3 carbons, okay? Glycerol is a backbone molecule that is used to make every lipid molecule, okay? We also see a fatty acid molecule. Now, this fatty acid molecule, we see a bunch of C's, that's for carbon, right? A bunch of H's, that's for hydrogen. I see a couple oxygens here and there as well in these two building blocks. But two building blocks, fatty acids and glycerol. Okay, so there's your answer for building blocks of a lipid molecule. Now in this particular lipid molecule that they've built here, they've taken, there is a fatty acid, long chain of carbons here, okay? Now I'd like to remind you before we go too much further, if I have a carbon and it's sharing electrons with another carbon, and we have a covalent bond, right? A sharing of electrons, that's what every one of these lines represents, then who's going to win that war between two carbons? Nobody, right? They're both going to pull for the electrons equally. So these covalent bonds between carbons, would it be nonpolar or polar? Which one is an even sharing? It would be nonpolar, right? So we have nonpolar covalent bonds holding these carbons together. There wouldn't be a lot of charge there, right? Electrons aren't being pulled one way more than another. This would be a relatively uncharged situation, right? There is no charge next to one of these carbons more than any other. So we're going to have, in this particular situation, a molecule that is not charged. Will that like to hang out in a water environment? Remember water? Remember water molecule has polar covalent bonds, right? We've got the two hydrogens. On the other side of this molecule, we've got our oxygen. We've got a positive charge on one side and negative charge on another. What do we know about fats? Oils being one kind of fat. They do not mix very well, do they? So this gives us a good reason, a good explanation as to why oil and water don't mix very well, right? All right, to make this lipid molecule down here, this fat molecule down at the bottom, okay, what they've done is they've shown how fatty acids, in this case 3 fatty acids, formed a bond, and guess what came out of this bond? 2 hydrogens and 1 oxygen atom. Dehydration synthesis. When 2 molecules come together like this in chemistry, well, water is oftentimes released. Because it is released, dehydrate, right? When you lose water, when water is lost in this event, we call it dehydration synthesis, right? This is pretty common when two molecules come together. We oftentimes see this OH group and another hydrogen, and they bud off as a water molecule. So we've had dehydration synthesis, fatty acids join, and then imagine that happening twice more, and we have 3 fatty acids and 1 glycerol backbone. All right, we've learned that this would be an insoluble situation. In other words, hydrophobic. Hydrophilic would be a salt in water, right? We have charged ions. They like to be in a charged environment. Here we have uncharged molecules, like this fat, like oils might be. And it is going to be insoluble in water, hydrophobic, okay? All right, so what would be a function? This is a major thing we need to know, right, about each category. Well, when it comes to fats, you could just kind of brainstorm, right? Well, fat actually keeps me warm. Yeah, you could. That would be one function of fats. You could say that fats are found around organs a lot of times, and they cushion organs. So if you look at internal organs, you see a lot of lipids around there, fats around there. So they cushion. But what I would say as a major function for a fat is that fats have a lot of energy. The more covalent bonds, and look at all of them in this long chain of carbons, the more energy. Every one of these covalent bonds represents a certain amount of energy we could get out of a fat. Think about your dog. If you have a dog and you buy them a bone, right? A bone shank, right? So it's got a bone and you have a lot of that white stuff in the middle, the marrow, and a dog goes crazy for that, the middle of the bone, right? It licks all that stuff out. That's because the fat has a lot of energy in it, okay? That's good stuff for the survival of an animal. So that's the big function I'd want you to know, even though there's a lot of others. A couple other things. Fats are essential for steroid hormones that we produce. A lot of the sex hormones are steroid hormones, even though you might think steroid and think about the anabolic steroids, right? The illegal steroids when it comes to weight, to bodybuilding and things like that. Cholesterol is actually fatty acids are a building block for cholesterol. And cholesterol, believe it or not, is a good thing in the body, unless it's too high in concentration. And even the cell membranes, the outer boundary of our cells in our body, have kinds of lipids that compose them. Okay? Okay, the last thing I'll mention before I leave this particular slide, we need to know the elements, right? We've got the name, lipids. We've got the building blocks, glycerol and fatty acids. We've got the basic functions. So let's take a look at what are some of the elements. I see a lot of carbons galore, right? I see a lot of hydrogens galore. And I see a few oxygens. So I would say, you want to know carbon, hydrogen, oxygen. CHO. Remember CHO, and you'll remember CHO, carbon, hydrogen, oxygen, for our lipids. All right, another thing that you hear out there when it comes to fats are saturated versus unsaturated. So let's look at this. Here we have, in the top here, we have some fatty acids, kind of like the last slide, and our glycerol. Well, if we look at this top fatty acid, I have a carbon, and I have, for almost every one of these carbons, I have pretty much 4 bonds. 1, 2, 3, 4. And along the way, 2 of these bonds will be with another carbon, but then the other 2 have hydrogens. If we talk about a saturated fatty acid, what we're saying is that every carbon in this chain has at least 2 hydrogen atoms bound. Now this last one, of course, has 3, right? But these carbons in the middle are saturated with hydrogen bonds. Each carbon can only make 4 bonds, and 2 of them are with hydrogen. Saturated fatty acid. Here's another saturated fatty acid here, okay? Down here, though, we have one set of carbons where we don't have a hydrogen sticking off of each of these carbons. This would be an unsaturated fatty acid, right? There aren't the maximum number of hydrogens bound to these 2 carbons here, so it's an unsaturated fatty acid. Okay, so we'd refer to this molecule down here where we bound then to glycerol as an unsaturated fat. Why? At least one of the fatty acids has this double bond, right? Two bonds form between these carbons instead of having hydrogens sticking off the side. Okay? So this will be the reason for saturated versus unsaturated when we talk about fats. All right. So what could happen if we take a fatty acid chain, right? Lots of carbons in a row. Now let's imagine what would happen if we took a fatty acid like that and we played a game with it and we just kind of made a shape out of that long chain. When I was a kid, we had something called a Rubik's snake. Okay, so this is probably something nobody your age has seen, but a Rubik's snake was a long, thin thing like this, and you could bend it and form different shapes like you see down here. Okay. Well, imagine now a fatty acid like that, right? A fatty acid, long chain of carbons. Whether it's unsaturated like this one or not, imagine taking this long chain of carbons and kinking it up and making a shape out of it like this, with every one of these little corners being a carbon. Okay, it's not representing all of the atoms, just the carbons here at these corners. This is a cholesterol molecule. So our fats are a base unit that are used to make cholesterol. Now you might say, well, cholesterol is bad. In our diet, I don't want too much cholesterol. And you'd be right. But cholesterol is an essential molecule in the biological system. And let me show you what some other molecules that look like this cholesterol are. So here we have cholesterol. And here we have a whole list of different molecules that look very similar. They just have little twists and turns, little changes if you look at them carefully as we go through here. And some of them are called testosterone, estradiol, which is basically estrogen. Maybe some of you have heard of some of these others, progesterone, for example, corticosterone, right? These are some natural molecules produced by the human body, and without these fatty acids, basic units that make up a fat, we would not be able to have these normal human steroid molecules. Okay? Last thing about lipids that I'll mention, here we have a phospholipid. Okay, so let's look down here. Here we have carbon, carbon, carbon. Glycerol right there, right? We have our backbone. And then we have this long chain of fatty acids, and we have another long chain of fatty acids. They just kind of shorten and they say, oh, there's 12 of them here, right? Well, they're not showing you the truth, right? This is much longer here than it may seem. These are our fatty acids. But our third carbon has this big chunk sticking off the side here, right? And it seems to have a charge here, a negative charge. So we're dealing with now a lipid, which we would say is hydrophobic, right? Here we have this side with the fatty acids where there's a lot of non-polar bonds, right? That means there's no charge there. Here's another rendition, right? These long chains would be hydrophobic. But up here, we see a charged situation. We would say that this phospholipid, the phospho part, see the P? Okay, that's the phospho, the phosphate, they actually call it, entity there, would give it charge. So we have a part of this molecule, this phospholipid, that has charge, hydrophilic, and a part of this phospholipid that does not have charge, and it doesn't like to hang out in water. This is a basic molecule found in our cell membranes. Okay, so basic molecules for energy, basic units for the cholesterol and some of our natural steroids, and a basic unit for making the boundary of our cells, these phospholipids. Okay? So I think I'll leave it at that for our lipids, and we'll dive into our other organic compounds next time. Okay? Starting with the carbohydrates.